All right, good afternoon, everyone. Going to go ahead and re-record section 3. I was told there were some slight inconsistencies with the with where the slides were. A couple other videos I might have to go back and redo, but I want to make sure there are no discrepancies and we're able to get through the material as best as possible. Now, our objectives again for section 3 will be for students to be able to recall and understand the 4 factors that affect the reaction rate, or rate of reaction, describe the parts of the collision theory, and recall and apply the definitions of the following terms, and they are listed below. Hopefully by this point you sort of have an idea of where you are when we cover these materials, but let's go ahead and get started. Now, as we talk about this, we're starting to go into the phase of chemistry that we call kinetics. Kinetics is concerned with how the molecules are actually moving, how do they interact. And the way that we'll discuss this, or that we'll understand this concept, is looking at the rate of reaction, which is just looking at how does the concentration of the reaction or reactants change over time as we go from reactant to product. We're going to notice that the concentration, of our reactants should be decreasing over time as our products are forming, and some of the things that will affect this process. Now, the first thing that we talk about here is we talk about the collision theory. This is our way of sort of explaining something that we can't see, something that's a little bit more difficult for us to see. In terms of how our particles and our molecules react, we know that 3 things have to occur. First off, they have to collide. There has to be some sort of interaction. I can't sit back and say, okay, here's a cup of one chemical or one molecule, and here's a cup of another, and expect that something will happen until they are able to bump into each other and to interact. The second part will be that they must collide at the correct angle. If I'm using an example here, if I have 3 points in which I have to make some sort of connection, and I have a molecule that's here, unless I hit at the correct point, I won't get a reaction. So if this person, say, was to knock into our person here on the end, we'll call this person 1, we wouldn't be able to have a reaction. That wouldn't work. But what would happen if they then hit one of the spaces where there's a bond formed? This is what we want to look at in terms of saying the correct angle. Now, the third part that comes into this is we can't just look at it and say, okay, now we have a reaction, or we bumped into that bond, so now everything should just break apart. We also have to make sure that we have enough energy in order to to break the bond and to be able to form a new bond, given to us by our example here on the side. Now, in your notes, you have a potential energy diagram given to you, and these are the main parts that we want to be concerned with. First off, always on the left side of our graph will be our initial energy of our reactants. This is the energy that's stored in the bond on our reactants. As we continue to go up, coming over to the other side, we're going to reach what's called our activated complex, or what we need to understand more so, what is our activation energy? What is the amount of energy that I have to put in at the end in order to get the reaction started? This will be my sort of like me lighting the match and dropping it in to the jug when we did our demonstration. Next, our last part here on the side, we're still on the right side, will be our final energy of our products. Once we've gone through our activated complex, once the reaction has gotten started and we've made our products, how much energy is stored in those bonds? Last but not least, we have what was our total change in energy. In our previous unit, we said that was our delta H. Since we have our delta H, that's going to be the difference between our final and our initial energy. Now, the reason why I say the final minus the initial is because this is also going to tell us whether we have a positive value or a negative value. If the value comes up as a positive value, then that means we know it was endothermic. If it comes up as a negative value, that means we are working with an exothermic system. And this is basically the thing that I was just telling you. So in our previous example, we noticed that our products, if I may go back, our products were lower than where we started. So since they are lower than where we started, that means I would end up with a negative delta H value, meaning it's an exothermic reaction. But if I have a positive value, in the situation we have here in the graph given to us here, means that it's an endothermic reaction. Now, what are the factors that affect our reaction rate? What can we do to actually speed up our reaction? And there are four main things that we're going to talk about. The first thing is to increase the temperature. By increasing the temperature, what we're doing is we're basically adding energy into the system to get the particles moving at a faster rate. The more they move around, the faster they move, the better chance we have that they're going to bump into each other at the correct angle with the correct energy that we need in order to get a reaction to take place. The second thing that we have the ability to do is to change the concentration. Concentration is the number of particles that are actually present. So if I want to increase the concentration, I may add in more of whatever reacting substances I have. This will increase the opportunity for them to actually bump into each other because now we're sort of in a crowded space. They can't help but sort of bump into each other. The third thing is going to be to change the particle size. If I have a block of any type of substance, which is given to you here at the bottom of the slide, the only place that I can have a reaction is here on the outside and on the top. Now, in our reaction, we want it to be able to go faster. So what we're going to do is we're going to break up this, and as you see in part B, now I can react from every side of our molecule. This is going to help the reaction to go much faster. It's going to also help it to be more efficient for us. That's one of our goals. Now, our fourth manner that we're going to use is to use a catalyst. A catalyst is used to lower the activation energy or to speed up the reaction rate. How is this possible? Well, the catalyst actually doesn't participate in the reaction. If you remember when we talked about our chemical reactions unit, I gave you this system. I said that when you see an arrow, but then it has a compound or an element written above it, that means that there's a catalyst present. Using our example from class of the decomposition of hydrogen peroxide, it's still going to break down into the same process, still going to make oxygen and water, but it's going to just happen faster. In the example that we have here in our graph, you see that the lower line of the pinkish line is the one that has a catalyst. Now that I have to put in less energy, the reaction can proceed much, much faster. This allows us in the world of business or in the thought of business to be able to make more of a product to get it out to the people who need it. Now, reaction mechanisms. One of the things that we've covered before, and there's actually a little bit more information that goes with it, is the fact that most reactions have multiple steps that they have to go through. Many times we present them as just one single step because it's easier at that point to understand what's going on. But as we continue to look through this, we'll see that to make it to what we call that activated complex, there are actually maybe several steps that have to happen. Now, the product that we make at each of these steps, or each of these points, shown by the dips in our graph, are called intermediates. These are going to be products from one reaction that are used up in the next step of the reaction. Many times you won't see them in the final equation, but they are part of the process of how we get from our reactants all the way to our products. Reversible reactions. Many of the reactions that we've talked about, and I'll post a link for the FET activity that you can go through to see what we can do in order to get a reversible reaction. A reversible reaction is going to be a reaction where we're converting from reactant to product at the same time as we convert from products to reactants. This can be due to pressure, it can be to temperature, and different things in the surroundings of this chemical reaction. One of the examples that we're going to utilize here is sulfur dioxide with oxygen. As these two things react, we're going to form sulfur trioxide. But at the same time, because this is a very unstable molecule, sulfur trioxide will begin to break down right back into the reactants. And this will happen at different rates. So don't think it's just I form one molecule and then it breaks down the next second. We'll have possibly thousands being formed at the same time as thousands are being broken down. The way that we're going to notice this, if you see it at the bottom of the screen, or I'll also put one right here on the side, is you'll see a little double arrow. And this will let us know that the reaction actually goes both directions. That is a reversible reaction. With the understanding of a reversible reaction, now we're actually going to get to what's called equilibrium or chemical equilibrium. Now, this is the point at which the rate of the forward reaction is equal to that of the reverse reaction. What do I mean? Most people will think when they hear equilibrium, it sounds like equal, like it's the same amount. But in actuality, it's really a point where we're making the same amount of progress forward as we are backward. So the change is equal, not the concentrations being equal. And this is what you see given by our different graphs here. In the first one, we're looking for the point at which each of our graphs level out and they begin to go straight. This means that they're being broken down and made at the same rate. To give another illustration, if I go to the mall, there may be different concentrations of people upstairs and downstairs. If I have 50 people upstairs, I may have 30 people downstairs. But at different points, I may have the same amount of people going upstairs as those coming downstairs. Because I have the change that is equal, that would mean that this would be a system at equilibrium. The same thing will happen with a chemical reaction. The goal is to remain at equilibrium as long as possible. But what happens when we change that? What do we do when all of a sudden something changes our equilibrium or brings us out of balance? This is what Le Chatelier was talking about when he developed what we now call Le Chatelier's principle. It says when stress is added to a system at equilibrium, the reaction will shift or change in order to ease that stress. This is going to be our main thing that we look at for just a few moments. Now, what can that stress be? That stress can be as simple as we turn up the temperature, we change the concentration, we change the pressure, or we even add a catalyst to continue the reaction in one way or the other. The overall picture is once we've shifted from that equilibrium, whether it be through any of these four, the reaction will try to find a way to work itself back to equilibrium. Just like us with our bodies, we are usually at a point of homeostasis. This is where our body wants to be, where everything functions as it should and everything is balanced. When we exercise or when something bad happens, our body fights and fights and fights to get back to that equilibrium point. Same thing will happen with our reaction. We're going to pick up our discussion in class. I hope that this was helpful, and let me know if there are any other questions that you need answered. Have a great evening, and good luck.